Hello guys, today I'll be explaining the chemistry CQD chapter 9 questions, not only the CQDs, just I will be explaining the note questions. So, in chapter 9 there's no no equations, so it's more logic than solving. Now, let's start. How is the rate of reaction defined? In the previous video, the one that I did the summary of chapter 9, we said the rate of the reaction is defined or measured or calculated in either the products produced per unit time or reactants consumed per unit time. Meaning, for CQD number 3, the options are A, decrease in concentration of product. No, as we said, the products are being produced, so their concentration is being increased. Okay, so is it B, decrease in concentration of products? No, we said an increase. Now C, increase in concentration of products per unit time. C is correct. Now a decrease in the concentration of reactants per unit time. This is also correct. So, how is the rate of reaction defined? It's either as the products produced per unit time or the reactants consumed per unit time, or an increase in the concentration of products per unit time and a decrease in the concentration of reactants per unit time. Now, calcium carbonate, CaCO3, and hydrochloric acid react as shown below. Choose the most suitable method to determine the rate of the reaction above. Okay, we said there are two different types of using the reaction rate. We can either measure or calculate it, or we can study and determine it. To measure or calculate it, it is the quantity of products produced per unit time or the quantity of reactants consumed per unit time. And to determine or study it, it is the volume of gas produced with unit time or the change in mass with time. So for CQD number 4, we need to choose the most suitable method to determine the rate of the reaction above. First of all, change in temperature of solution with time. We didn't say anything about the temperature of the solution, so definitely A is wrong. B, the change in volume of carbon dioxide gas with time. First of all, we said to study, it's here in 3, to study the rate of a given reaction, we use the volume of a gas produced with time. That means it has to be in the products, it cannot be in the reactant. So let's see, is carbon dioxide in the products or in the reactants? It is in the products. So definitely we can use the change in volume of carbon dioxide gas with time. Now, the change in mass with time only works for solids, so you cannot use the liquids or aqueous solutions to determine the change in mass with time. We can only use the solids. So C, which states that the change in mass of water is H2O. H2O is a liquid, so we cannot use it. And then finally, the change in concentration of hydrochloric acid with time. We did not say that if we're going to determine or study, we didn't say that we would have to do anything with hydrochloric acid. So for CQD number 4, B is the correct answer. CQD number 5, here it seems the answer is already given to us, but let's solve it. Calcium carbonate, CaCO3, and hydrochloric acid, HCl, react as shown below. It's the same equation as above. The mass of the apparatus used and its contents is plotted against time. Choose the graph that shows what happens to the mass in time as calcium carbonate reacts with excess acid. If the acid is in excess, that means the calcium carbonate is limiting reactant. Now this information is not relevant to what we're discussing here. I'm just gonna give it as an indication. You have to pay attention to these stuff and when you will use these stuff. Okay, so if the excess acid, so the HCl is excess, then definitely the calcium carbonate, which is the CaCO3, will be limiting. Now we're gonna choose the graph that shows what happens to the mass of CaCO3 plotted against time. Now, CaCO3 is what? It is a reactant. So definitely the mass of the reactant is gonna decrease over time because it's being used up. So if the mass of CaCO3 is to be plotted against time, it will decrease like this. So it will start high, then it will decrease, and at some point it will be a straight line. Why is it a straight line? Because it is used up. Okay, it's fully used up. Now, if we were talking about products, however, if we are doing the mass of products plotted against time, for example, the CaCl2, or no, we cannot do the CaCl2 because it's aqueous. If they gave us a solid product and they told us to graph what happens to the mass in time of this solid product, it will be as such. It will increase, and then it will be a constant slope. So again, we have this equation. They need us to find the mass of calcium carbonate, which is limiting, okay? Because the excess is the acid. The only time we can use the mass is if it's a solid. So here CaCO3 is a solid. So if it is in the reactant side, the mass will decrease until it stops, all right? However, if it is in the product side, the mass will increase until it stops. So that's it for CQD number 5. CQD number 6. Calcium carbonate, CaCO3, and hydrochloric acid, HCl, are shown. React as shown below. Okay? It's always the same example. So, which diagrams would be suitable for studying the rate of this reaction? We said, to study the rate of this reaction, we need what? We need to either measure the volume, okay, of gas. This is of gas produced, or the change we're studying, or the change in mass. So, to measure the volume of a gas, we're gonna use what? We're gonna use a syringe. Now, definitely, if we are using a syringe, we need something to stop the gas from escaping. So if you're gonna use the syringe, are you gonna use a cotton wool that will let the gas escape? Definitely not. So we're gonna use a stopper. If we're using a syringe, then we can use a stopper. This is to measure what? The volume. Now, to measure the mass, the change in mass, what do we need to do? We need a balance to weigh, okay? And we also need the gas to be released. So for the gas to be released, we need to use a cotton wool. So we can think of it like this. Anytime we see a syringe, it has to be accompanied by a stopper. And anytime we see a balance, it has to be accompanied by a cotton wool. So the two correct answers here are 2 and 3. CQD number 1. Which of the following affects the rate of a chemical reaction? We said in the previous video, what affects the rate of a chemical reaction? The surface area, the temperature, the concentration, the nature. I didn't state it there, but the nature means as in solid, liquid, gas, aqueous, okay? And the catalyst. And then only for the gas, the volume and pressure affected. So, in general, if they're talking in general about the rate of a chemical reaction, we're not going to take the gas by itself or the liquid by itself or solid by itself. No, we're going to take in general, we're going to take all the factors that could possibly affect a chemical reaction. Okay? So, and if they don't specify what type of chemical reaction it is, we're going to say it's solid, liquid, aqueous, and gas. Okay? So definitely the concentration of reactants affect the chemical reaction. Definitely the pressure of gaseous reactants affect. Definitely the surface of contact in heterogeneous systems or solids affect. Definitely the temperature affect. Definitely the nature, meaning if it's solid, liquid, aqueous, or gaseous, will affect. And finally, the catalyst will for sure affect it. So our answer is all of the above. Now, CQD number 14, good. What are the factors that affect the rate of a chemical reaction and how do they affect it? Okay, let me go up because there's more space. Okay. Let us list all the factors one by one and how they affect. We have, first of all, the concentration. If we increase the concentration, then the particles will increase, the number of particles will increase, thus effective collisions will increase, and that leads to what? An increase in the reaction rate. So that was what? For the very first thing, which was concentration. Now, they didn't specify what type of reaction, so we're gonna state them all. The second thing is the temperature. Okay, if we increase the temperature, then the kinetic energy of particles will increase, thus causing the effective collisions to increase, and then the reaction rate will increase. That was number 2, the temperature. Now we have number 3, which is the surface area. If we increase the surface area, this is only for the solids or heterogeneous systems. So if we increase the surface area, then the particles will be more spread out. And since they are more spread out, this will increase the effective collisions. And since the effective collisions increased, the reaction rate will consequently increase. For number 4, I will put 2 in the same one because they affect both of them the same way. We have the pressure and we have the volume. If we increase the pressure, then the volume will decrease. However, if we increase the volume, then the pressure will decrease. But let's take into consideration now that the pressure is increased and the volume is decreased. What will happen in this case? The effective collisions will increase. Why will they increase? Because since the pressure increased and the volume decreased, the gas particles come closer together, so they're more likely to collide. So the effective collisions will increase, thus the reaction rate increases. Now for the last one, which is number 5, it is the catalyst. What about the catalyst? Basically, if you add the catalyst, so we're gonna say if you add catalyst, then the reaction rate will increase. That was it for CQD number 14. Now CQD number 18. What is the effect of increasing the concentration of a reactant on the rate of a reaction? Justify your answer based on the collision theory. So, what does the collision theory state? The collision theory, I think we took it, I think I wrote it in the previous video. Okay, so the collision theory states that for a reaction to happen, the particles must collide with a minimum energy called the threshold or the activation energy. Now what happens if you increase the concentration of a reactant? As the concentration, I think we discussed it up, as the concentration increases, the particles will increase, the number of particles will increase. Then what happens? The effective collisions increases, and then consequently the reaction rate will increase. CQD number 22. Consider 2 gases, A and B, in a container at room temperature. What effect will the following changes have on the rate of reaction between these gases? If the pressure is doubled, remember we said that the pressure is inversely proportional to the volume, so then consequently the volume will be halved. So the pressure, we multiplied it by 2, the volume we divided by 2, okay? So definitely we said if the pressure increases and the volume decreases, then there is an increase in the concentration, and not more like the concentration, more like they are closer together, so it's more effective. So if the pressure is doubled and the volume is halved, they are closer together, so they will bump into each other more. Okay, so then there is more efficient, so increase in efficient collisions. So then there will be an increase in the reaction rate. For part B, the number of molecules of gas A is doubled. Gas A is a reactant, so if we double the number of molecules of gas A, then we are increasing the concentration. So we're increasing the number of particles, and if we're increasing the number of particles, then definitely there will be an increase in the effective collisions, and then the reaction rate will increase. Part C, the temperature is decreased at a constant volume. So since the volume didn't change, but the temperature is decreased, a decrease in temperature will slow down. So slows down effective collisions. So since they are slowed down or they decrease, okay, we say that the reaction rate decreases. That was for CQD number 22. Now CQD number 16. What is the effect of increasing temperature on the rate of a reaction? So as we increase the temperature, there's gonna be an increase in the kinetic energy, or the energy of the reactants, okay? And if the kinetic energy increases, they are more likely to bump into each other, so there's an increase in successful or effective, however you like to name it, successful collisions. Okay, and thus this results in an increase in the reaction rate. Now, CQD number 2. When magnesium ribbon reacted with excess dilute hydrochloric acid, so the hydrochloric acid is in excess. All right, that means the magnesium ribbon is the limiting. Okay, the total volume of hydrogen produced was noted every 20 seconds. The results are given in the graph labeled C as drawn below. So this is our graph labeled C. Part A. They're telling us which of the graphs A, B, D, or E would have been obtained if a leakage of gas occurred during the experiment. Definitely, by looking at E, you see there's an increase in the beginning, then everything stays the same. So definitely there was a leakage. So E is the leakage of gas during the experiment. Then for part II, we have only half the magnesium ribbon had been used compared to as with the original amount used in C. C is the original graph, okay? So they're telling us half the amount of magnesium ribbon. So the concentration of the limiting, because we said magnesium ribbon is the limiting, decreased because we used half the amount. And because the concentration decreased, then what happens? Then the slope, if you remember I explained there, if you decrease the concentration of a limiting, then the slope plus the plateau get affected. So in which graph are the slope and the plateau affected? They are in A and D, but we're gonna take D. Why? Because it has to be lower, it should be less than the original graph. So definitely for part II, the answer is D. Now for part III, slightly warmer excess acid has been used. So the hydrochloric acid, I think, or let's just say the excess acid, they increase the temperature. So an increase in temperature will increase the reaction rate. But we know that the temperature only affects the slope. So which graph the slope is only affected? It is B. So definitely our answer for III is B. Now for IV, Okay, they're telling us a greater mass of powdered magnesium. Powdered magnesium is what? It's our limiting. So if a greater mass is used, that means the concentration of our limiting has increased. And we said that the limiting, if you increase or decrease the concentration, the slope of the plateau, the slope and the plateau, will be affected. So in which graph are the slope and the plateau affected? We have D and we have A, but we're gonna take A. Why? Because a greater mass of powdered magnesium was used, so we need to be greater than the original graph C. So in order, our answers are E, D, B, A. Now, what was the final volume obtained in experiment C? So we're going to go to experiment C. We're going to see where is the final volume. It's over here. Why? Because here it starts to decrease. Like the rate starts to decrease slowly and then it becomes constant. So at this point over here, so we're going to say it is approximately 60 centimeter cubed. That was it for CQD number 2. Now, exercise number 1. Which mixture will produce the slowest? They don't need the fastest, they need the slowest reaction to take place between solid barium carbonate, chips, and dilute hydrochloric acid. Solid, what affects the solid? The surface area. And the hydrochloric acid is a solution. What affects the solution? The concentration and the temperature. So, let us see which of the following will produce the slowest reaction. If we have low temperature, large chips, so look, surface area, if you increase the surface area, the size becomes smaller. However, if you decrease the surface area, then the size becomes larger. So, which mixture will produce the slowest reaction? Low temperature, large chips, and concentrated acid. This is correct, but this is wrong. This will produce a faster reaction. How about low temperatures, large chips, and dilute acid? This B possibly works. High temperature, directly from the start, wrong. And then high temperature again, directly from the start, wrong. And then again, high temperatures directly from the start, it is wrong. So our answer for exercise 1 is B, to produce the slowest reaction. Now, exercise 2. Okay, iron reacts with HCl to form iron dichloride and hydrogen gas. 2 grams of iron is added to 100 centimeter cubed of dilute hydrochloric acid. Which conditions produce the fastest reaction rate? So we need a fast reaction rate. Let's read the options. We have iron powder at 50 degrees Celsius. So here has a large surface area and a large or a big temperature. So A could possibly work. B has a small surface area and a high temperature, so it won't produce as fast as A. So B, we're gonna cross it out. Then C, we have small surface area and low temperature. Definitely it will not work. For D, we have a high surface area and a low temperature, so as well it will not work. Like it will work, but it won't work as well as A. And then E, we have a high surface area and again a low temperature. So definitely E will not work and A will provide us with the fastest reaction. Exercise number 3. Oh my goodness, okay. For reactions to occur, the particles of the reactants must collide. Which of the following decreases the frequency of collisions between reactant particles? So breaking the solid into smaller pieces in a reaction involving solid and liquid, yes, definitely. If you break the solid, it will it will work more. It will work more and it will increase the frequency of collisions. But this isn't what we need. I didn't read the question, sorry. Okay, decrease the frequency of collisions. Don't do like me and not read the question. No, read the question. So they said, which of the following decreases the frequency? We said the first one. It will increase the frequency of effective collision, so it is wrong. Raising the temperature of the reaction mixture, it will increase, so it is wrong. Decreasing the concentration of a reactant. It depends which reactant, but in general, yes, if you decrease the concentration, then yes, the frequency of collisions decreases. Then, increasing the pressure for the reactants involving a gas, it will increase the reaction rate, so we do not take it. And finally, decreasing the temperature of the reaction mixture will decrease the reaction rate, so we will take it. So for exercise 3, we have C and E. Now, CQD number 13. Explain why there is danger of explosion where a large amount of dry powdered combustible material is produced. What do they mean by combustible? Combustible means it reacts with O2. If it's dry and powder, that means it has a large surface area. And we know that if we have a high surface area, a large surface area, then it's more prone to reacting faster. So it will react faster with the O2, and because it's reacting faster with the O2, it will cause a danger of explosion. So again, I will re-explain it. We have a large amount of dry powder, that means we have a big surface area, a large surface area. Combustible means it will react with O2 material. So because they are like very tiny particles, they have a large surface area, they will react faster with the O2, and then they will produce an explosion. Now for part B. Explain at the molecular level why an increase in the concentration of a reactant may cause an increase in the rate of reaction. So we said many times, we said before, if we increase the concentration, then the number of particles will increase, and since these number of particles increase, then the rate of effective collisions increases, and then consequently the reaction rate will increase. So now CQD number 21. Which of the following is the activation energy? Activation energy, another name for it is threshold energy. So, the maximum amount of energy that the particles need to produce effective collisions? No, this is not the definition of activation energy. The amount of energy used by particles during a collision, this is also not the definition of activation energy. However, it is the minimum amount of energy required by reactants to undergo a reactant. C is correct. It's the minimum amount of energy which the reactant molecules must possess for effective collisions in forming the products. This is true, but you have to pay attention in how it is worded. It's saying it's the minimum amount of energy that the molecules must possess. This is a very tricky statement, even though it is correct if you, in the sense of it, there's this word must possess is incorrect. It should not possess, it is required for it to have. There's a difference between possession. So for example, like, in physics, I know I'm bringing physics and chemistry, I shouldn't be, but like we have the gravitational potential energy. It possesses gravitational potential energy, that means it stores it in this sense. This is how I think they are meaning it. So which of the following is the activation energy? It is the minimum amount of energy required by reactants to undergo a reaction, or if in the exam they give you it is the minimum amount of energy with which the reactant molecules must gain, not possessed, must gain for the effective collisions in forming the products. Possess can mean that they have it from before, but no, they need to gain it or they require it. Anyways, if you read the definition over here, activation energy is the minimum amount of kinetic energy that must be overcome. They didn't say possessed, that must be overcome. So you have to either have this minimum amount or greater than this minimum amount for the chemical reaction to occur, or it is the minimum kinetic energy or the minimum amount of energy that the reactants should collide with. They didn't say that they need to have possessed it. No, they should not possess it. They should gain it. They should take it from, or like, it's the minimum that they should have, not possess, the minimum they should have. So for CQD 21, it may be a little confusing, but please pay attention to the wording. In the exam, if they will tell you activation energy, no, it's the minimum amount of energy that is required, must be overcome means required for a chemical reaction to occur, or it's the minimum kinetic energy that is needed okay, for the reactants to collide with each other so that they can react to form the products. So that was it for CQD number 21. Now we have CQD number 19. Study the following potential energy diagram and answer the questions below. So we have to label A to K. First of all, it said it's a potential energy diagram. In the potential energy diagram, on the y-axis, it is the potential energy. However, on the x-axis, it is the reaction coordinates. So remember, anytime they tell us potential energy diagram, it is the potential energy is on the y-axis and the reaction coordinates, that means their location where they are, is on the x-axis. Now we labeled A and B. C, if you remember from chapter 8, if we have this such diagram, then here is the reactants and here is the products. So C is our reactants and D is our products. Now, what letter comes after the E? So for E, it is the energy, or not the energy, we can say the heat or the potential energy. So what letter comes after D? E, okay? So E, we can name it either the heat of our reactants or the potential energy, we will call it PE of our reactants. After E comes F. F is the same thing but for products, so it's the heat of products or the potential energy of products. And then after F comes H. No, sorry. After F comes G. G is our forward reaction. Now after G comes H. H is our backward reaction. So think of it like this. If it is closer to the reactants, it's the forward reaction. If it's closer to the products, it's the backward reaction. Now, what comes after H? I. This is I. I is called the activation energy. What comes after I? J. J is the distance. Let me choose a different color. J is the distance between the reactants and products, and this distance between the reactants and the products is called the delta H, or the enthalpy change. And then finally, we have the last letter, which is K. K is our activated complex. So I know drawing on the diagram is too much, so let me label each one of them. So here we go. I wrote each one of them, what they are. Now they're telling us calculate the values of E to J. So first of all, E is the heat of our reactant. To calculate it, we're gonna take it from the bottom. The bottom over here is 0. And then we're gonna go all the way to where it stops. So the value of our E, there we go. The value of E, which is the heat of reactants, okay, it is plus 525 kilojoules. Why do we say it's plus? Because it's going from the bottom all the way to the top. Now F is the heat of our product. So again, we're gonna go from the bottom all the way to the top. So it's gonna be plus, since it's starting from the bottom and going to the top, it's gonna be plus 175 kilojoules. Now after E we have F, after F we have G. G is our forward reaction. It's the forward activation reaction. So to calculate the value of G, we're gonna take where it ends and we're gonna subtract it from where it started. So it's gonna be 788 minus 525 if we do it on our calculators. 788 minus 525. We will get 263, but we will put it as positive. Why? Because it's going in the upwards sense. After G comes H. H is now the backward, it is the backward reaction. Okay, so since it's going in the upward sense, we're gonna take it as positive. So wait, it is now, we're talking about H. H is the backward. Since it's going in the upward direction, we'll take it as positive sense. And so then we'll take from where it starts and where it ends, and we're going to subtract them. So it's going to be 788 minus 175. So let's do it on a calculator. It's going to be plus 613. And now finally we have J. J is going in the downward sense, so it is negative. Okay. So we will take from where it started, like it starts from 175 actually, and then it ends at 525. So it's gonna be 175 minus 525, so we will get negative 350. So that's how we know it is negative. Another way of knowing it's negative is because it goes downward, okay? So then our answer is negative 350. So is this an exothermic or endothermic reaction? Back to chapter 8. We said if our delta H, J is our delta H, okay? We said if our delta H was less than 0, it was exothermic. However, if our delta H was greater than 0, it is endothermic. So since our delta H, which is J, is negative 350, we say it is an exothermic reaction. So that's it for CQD number 19. So that was for CQD number 19. Now CQD number 20 is similar, but instead of exothermic, we're gonna be doing endothermic. So let's start. Let's label from A to K. A, as we said before, is our potential energy. B, as we said before, was our reaction coordinates. C is our reactants. D is our products. Let me use a different color. E is the heat of reactants. F is the heat of products. G is the forward reaction. J, no, not J. Actually, J is our delta H. Okay, then I'll explain each one why. And finally, H is our backward reaction. Now from A till D, I think from A till F actually it's very simple. It's the same in both, okay? Oh, I forgot to label the I. I is activation energy. Okay, so from A till F it's the same, and A to F is the same in both exothermic and endothermic. All right, but here G, we said the distance from the reactance energy all the way to the activation energy, we call this the forward reaction. And then the distance from the reactance energy to the product's energy, we would call this our delta H. So look, in red, this is the distance of our reactance energy. And again, in red over here, I can't draw a straight line, oh my goodness. Here, this is the distance between the reactant's heat and the product's heat. So we label this as delta H. And then finally, we said the distance from the product's energy to the activation energy is called the backward reaction. So that was for part A. For part B, we need to label from E to J. So E was the heat of our reactants. What is the heat of reactants? It's from down, which is 0, to the top. So it's 300 plus, because it's going in the up direction, it's going to be plus 335. Now, F is the heat of our products. Again, it's going in the upward sense from 0 to 468. So the heat of our products is positive 468. Of course, it is in kilojoules. Now, G is our forward reaction. G, forward reaction. The heat of G is the distance from 335 kilojoules to 526 kilojoules. So because it's going in the upward sense, it's positive, so plus, okay, 526 minus 335, so then it will give us 191 kilojoules. That's for G. Now let's find the value of H. H is our backward reaction, and because it's going in the positive sense, it's gonna be plus, okay, 526 minus 468. So if we do it on our calculator, it's gonna be plus 58 kilojoules. Now, finally, for J. J is our delta H, and because it's going in the upward sense, it is gonna be positive. So it's positive 468 minus 335. So it's gonna be 468 minus 335. It's gonna be plus 133 kilojoules. Now they want us to say, is this endothermic or exothermic? We know if delta H is less than 0, it's exo. However, if delta H is greater than 0, then it is endo. In our case, it's plus 133, which is greater than 0, so then this is an endothermic reaction. If you're not sure, you can always check if the reactance is lower than the product, then it is endo. However, if like in here, if the reactants are higher than the product, then it is exo. So that's it for CQD number 20. Now exercise 4. A catalyst speeds up the reaction, but I said in the previous video, when we talked about a catalyst, what does it do? The catalyst will increase the reaction rate, okay, without being consumed. Alright? On top of that, the catalyst provides a new pathway. How? By lowering activation energy. So let's do it like this. Okay? So the catalyst will increase the reaction rate without being consumed. It provides a new pathway by lowering the activation energy. It also speeds up forward and backward reactions, although it doesn't affect delta H. And of course, in the end, it's regenerated, basically that it's without being consumed. So, a catalyst speeds up the reaction by reacting with the reactants to form new products that do not need so much energy to form? No. By replacing the mechanism of the uncatalyzed reaction with a new mechanism that has a lower activation energy. This is correct. So it provides a new pathway. Replacing the mechanism with a new mechanism means that it's providing a new pathway that has a lower activation energy. C. Providing an additional path of lower activation energy so the catalyzed and uncatalyzed reactions proceed simultaneously. There's no difference between catalyzed and there's nothing to do with catalyzed and uncatalyzed reactions. So it's gonna produce not an additional, it will produce a new, not additional, a new path of lower activation energy, and the uncatalyzed reactions will not occur, only the catalyzed ones will occur, so C is wrong. A catalyst speeds up the reaction by slowing down the reverse reaction so that the result is a faster forward reaction. No. We said that a catalyst will speeds up forward and backward reactions. Okay, so the backward means reverse in this case. So you do not slow down, you are speeding it up. So D is wrong. And now finally, providing energy to the reaction so that the net activation becomes lower. Yes, this is true. So again, A catalyst speeds up the reaction by replacing the mechanism of the uncatalyzed reaction with a new mechanism that has a lower activation energy, by providing energy to the reaction, so the net activation energy becomes lower. So the only two correct are B and E. Now, what does a catalyst speed up? The catalyst speeds up a reaction by lowering the activating energy of forward but increasing the activation of energy of the backward? No. A catalyst speeds up the forward and backward reaction. Okay, so it doesn't lower the activating energy of one but increase the activation energy of the other. No, it will actually lower the activation of both the forward and the backward. If it's lowering, that means it's speeding up the forward and the backward reaction. So A is wrong. A catalyst speeds up both forward and reverse reactions, yes, but by lowering delta H? No, we said that the catalyst does not affect delta H. The catalyst speeds up the forward reaction without affecting the reverse? No, it will speed up the forward with speeding up the reverse. It will speed up all reactions by lowering H reactant, H product, and delta H. No, it will not affect the heat of the reactant, it will not affect the heat of the product, and it will not affect delta H. Finally, E, both forward and reverse reactions, yes, by lowering the activation energy of the forward and backward reactions. So E is our answer. So we can say a catalyst speeds up both forward and reverse reactions by lowering the activation energy of the forward and backward reactions. CQD number 17. So the graph below shows the differences in the rate of a reaction at different conditions. Indicate which of the following curves, A or B, is associated with a lower temperature, a higher concentration, a greater rate of a reaction, a smaller surface area, and the addition of a catalyst. Remember, we said sometimes the concentration, if it's not of the limiting, okay, if it's not limiting, it will affect only slope. However, if the concentration was of the limiting, it will affect slope plus the plateau. So here in this case, they didn't tell us if anything is limiting or not. So then we're just gonna say that a lower temperature will definitely lower the curve, so B. A higher concentration, they didn't tell us it was of the limiting, so for now we're gonna assume it's of the excess. Since it's of the excess, the higher concentration will only affect the slope. So A greater rate of a reaction, it will increase the slope, so A smaller surface area, it will decrease the reaction rate, so B, and the addition of a catalyst will increase the reaction rate, which is A. Again, a lower temperature will decrease the reaction rate, so B. A higher concentration will increase the reaction rate, so A. A greater rate of a reaction will increase the reaction rate, definitely, so A. A smaller surface area will decrease the reaction rate, so B. And the addition of a catalyst will increase the reaction, so A. Now, CQD number 15. In 3 different experiments, equal masses of calcium carbonate were reacted with the same volume of hydrochloric acid. In each experiment, one factor affecting the reaction rate was changed. The volume of carbon dioxide was released every 5 seconds, and the following graphs show the results. Here it's not clear which one is the excess and which one is the limiting, but we have equal masses of calcium carbonate, okay, reacted with the same volume of hydrochloric acid. So let's find the molar mass of CaCO3. It is then, it's almost 100, and then for HCl it is 36.46 grams per mole. So if they're saying equal masses, then definitely hydrochloric acid in this case would be the limiting reactant. So in this case, calcium carbonate is our excess and hydrochloric acid is our HCl. Now, since we know this, we are gonna fill in the blanks. A lower temperature, we said the temperature only affects the slope, all right? So definitely a lower temperature will have a lower slope but the same plateau, so B. A lower concentration of hydrochloric acid, we said HCl was our limiting in this case. Alright, so since it's our limiting, we're doing a lower concentration, both the slope and the plateau will be affected, so it will be C. Then, a smaller surface area of calcium carbonate, definitely the surface area only affects the slope. So a smaller surface area will have a less slope, so B. And finally, the addition of a catalyst. Definitely the addition of a catalyst will increase the slope, so it is gonna be A. So this is it for CQD number 15. CQD number 7. The graph below shows the volume of oxygen gas formed during the decomposition of 50 centimeter cubed of hydrogen peroxide solution using 1 gram of the catalyst. Give one possible reason why the point X at 15 seconds is not on the graph line. One possible reason is that if the scientist or the student is like not paying attention, he will read it wrong. So we call this an experimental error. He read it wrong. B. What volume of oxygen gas is collected after 20 seconds? So at 20 seconds, the volume was 30 centimeter cubed. How long does it take to collect 40 centimeter cubed? At 40 centimeter cubed, it's here. So let's say this is 30. This is approximately, I would say 32 to 33 seconds. So how long does it take to collect 40 centimeter cubed of oxygen? It's between 32 and 33 seconds. When the reaction stopped, it stopped over here. 1 gram of the catalyst was still left. What caused the reaction to stop? Okay. What would possibly cause a reaction to stop? What would cause, in other words, sorry, I dropped my pen. What would cause the reaction to finish? To stop, aka finish. Okay. The reactants were totally consumed. So again, a reason for the error was it's an experimental error. He read it wrong. B is 30 centimeter cubed. C is between 32 and 33 seconds. And D, the reactants were totally consumed. That's for CQD number 7. CQD number 8. A student added 10 grams of powdered CaCO3 to acetic acid. Acetic acid is excess, so CaCO3 is limiting. Okay, at 60 degrees Celsius. CO2 gas was produced and collected in a syringe. The volume of the gas was measured at regular time intervals. The results obtained are shown below. They need us to sketch on the same set of axes the shape of the curve you expect to get if the following changes were made. Okay. They're telling us in A, 300 centimeter cubed of 4 molarity ethanoic acid was used. I don't think they mean ethanoic. I think they mean acetic acid. Alright, so I don't think they mean ethanoic. They probably mean acetic acid. So, what happened here? We increased the concentration and we increased the volume. So, but we increased it of what? Did we increase it of the limiting or the excess? We increased it of the excess. So the excess, if we increase the concentration, okay, of the excess, the what's it called? The slope only is affected, okay? Whereas if we increase the concentration of the limiting, it would be the slope S plus the plateau, P. So we can see for part A, okay, the slope is increased. Now, so then we can say for part A that the slope is increased. For part B, sulfuric acid of the same volume and concentration was used. Label your graph B. So sulfuric acid all right, is definitely, I suppose, stronger than acetic acid. So since it is stronger than acetic acid, and we use the same volume and concentration, just because it's stronger, and of course we're gonna be replacing it instead of the acetic acid, so it's gonna stay on excess. The only thing it will affect is the slope. So the slope is increased. The acid was cooled before the reaction. If we cooled the acid, okay, the temperature will decrease. But since it is like, in general, the temperature will only affect the slope. Okay, so since the temperature decreased, the reaction rate will decrease, thus the slope will decrease. For 10 grams of CaCO3 in the form of small pieces were used. So we did not change the concentration, we did not change the number of molecules of CaCO3. Instead, we changed the surface area, and the surface area only affects the slope. Since we used small pieces, okay, and not large pieces, we are increasing the surface area, so thus the slope will increase. For part E, a catalyst was used. Definitely when we use a catalyst, the slope will only increase. Now focus please for part F. 12 grams, we increased the mass, so we're increasing the concentration of CaCO3 was used. The acid is still in excess, so that means CaCO3 is the limiting. Whenever we increase or decrease the concentration of the limiting, both the slope and the plateau are affected. So if we are gonna draw it, let's choose a color for each one. Let's say for A, we're gonna take red. For B, we're gonna take blue. For C, we're gonna take pink. For D, we're gonna take green. For E, we are gonna take yellow. And then for F, we're gonna take black. Let's use these colors to draw. First thing, we said here that the slope will increase. Why will the slope increase? Because we increase the concentration here. They're meaning acetic acid. They're increasing the concentration of the excess, and if we increase the concentration of the excess, it will only affect the slope. So this is what it will look like. For B, we said it will increase the slope because we used a stronger acid, but of course it's still the limiting, so it's gonna be similar to part A. Then for part C was in pink. We said the acid was cooled, so the temperature was decreased, so the slope is then decreased. So part C will be something, no, not like that. It will be somewhat like this. Okay. Then let me draw it better. Hold up. Let's say this is part C. Then part D will be in green. We increased the surface area, so that means we're increasing the slope. Part D is going to be similar to A and B. So let's say like this. All right. Part E in yellow, we used a catalyst. So of course, the slope is going to increase. It's going to look like this. And finally, we increase the concentration, so not only the slope will increase, but also the plateau. So it's going to be something totally different, which is probably, it looks like this. So this was CQD 8. Now we are CQD 9. A student carried out the following reaction to study the speed of reaction between zinc and hydrochloric acid. Zinc is in excess, so hydrochloric acid is limiting. Okay, the excess zinc powder was reacted with 50 centimeter cube of dilute hydrochloric acid, and the experiment was carried out at 25 degrees Celsius. The volume of the gas was measured every minute for 6 minutes, and the graph below was drawn, blah blah blah. Okay, so at what time does the result appear to be inaccurate? At what time does the result appear to be inaccurate? It's the only point that's not on the graph, which is at 2 minutes. Now, how does the speed of the reaction change over the 6 minutes? So it increases until here it starts to slowly decrease, and then finally it stops. But it stops not because of the reactants are completely used, but because the HCl, which is our limiting, was completely used. So not both reactants were completely used up, no, only the HCl was completely used up. Now for part C, sketch on the grid the graph you would expect if the experiment was repeated at 50 degrees Celsius. At 50 degrees Celsius, the plateau stays the same, but the slope is steeper. And then, I want to see if the white works. No, the white one isn't that visible. And then, using excess lumps of zinc, you are not really doing anything. You're just gonna be decreasing the reaction rate because there are more things to be to be reacted with. Now, when did the reaction finish? The reaction finished at here approximately, so we will say, no, not there, more of here. So this is around 3.7, 3.8. So the reaction finished between 3.7 to 3.8 minutes. Okay. Why? Because the HCl was completely, HCl is our limiting, it was completely used up. So, E. Explain using the collision theory why the reaction rate decreases. So, according to the collision theory, as the time will go, okay, the initial concentration of the hydrochloric acid decreases. So, basically, as we go throughout the time, the HCl concentration will decrease. So, concentration of HCl will decrease, and because the concentration of the limiting decrease, then the concentration of particles or the number of particles will decrease. Okay, and then the frequency of effective collisions decreases, thus resulting in the reaction rate decreasing or like slowing down and then finally stopping. Now, what's the purpose of the gas syringe? The gas syringe is to measure the volume of the gas. Now, how do we measure it? It's accurately. Why? Because we could use anything else to measure it. It won't be as accurate as the syringe. So we use the gas syringe to measure the volume of the gas accurately. Now, CQD 10. A student carried out the following experiment to investigate the speed of the reaction between sodium thiophosphate and dilute hydrochloric acid. Alright. A 100 centimeter cubed beaker containing 50 centimeter cubed blah 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 was placed on the black cross. Okay. Were added and the clock was started, the experiment was carried out. Initially, the cross was clearly visible. When the solution became cloudy and cross could no longer be seen, the clock was stopped and the time was recorded. Why is it necessary to keep the total volume the same in all experiments? It is for an accurate and a fair experiment. Alright, for accurate and fair experiment, or to compare them accurately and fairly. If the experiment is performed at 42 degrees Celsius, explain using the collision theory what happens. Okay, so we did it at which temperature? At 20 degrees Celsius. So we're increasing it from 20 to 42. Definitely there will be an increased effective collision. And due to the effective collisions increase, the reaction rate will increase. C. Why does the cross disappear on the paper? Because when we are forming it, when we are doing this reaction, what happens? It will form something cloudy, okay? This is cloudy. Why? Because we formed a solid sulfur. And what do we call it when we form a solid in an aqueous reaction? We call it a precipitate. This is from last year. So what can we say for letter C? Why does the cross on the paper disappear? Because it is covered by the cloudy formation of solid sulfur precipitate. That's for C. For D, the experiment was repeated using 250 centimeter cubed instead of the 100 centimeter cubed. How would the results differ? We are increasing the volume. We said if we increase the volume, what happens? The reaction rate would be slower, or in this case, because we're increasing the volume, also the surface area of the bottom will increase. So look, this is our beaker, for example. If we increase the volume, definitely it will be, for example, like this, like this, like this. So this was 100 centimeter cubed, then this became 250 centimeter cubed. So definitely it will have a wider bottom, a larger surface area at the bottom. And so this would be our x now. Instead of our x being smaller, it would be like this. If we kept everything the same, they would happen slower, and then to cover the x with the gas, it would take a longer time. So in short, the time needed for the cross, or the time for the cross to disappear would be longer. Okay, why? Because the bottom will have a larger surface area and the precipitate form will take a longer time to form. That was for which CQD? CQD 10. Now CQD 11. Dilute HCl acid was added to excess calcium carbonate. So this is our excess, this is our limiting. Alright, and a gas was produced. The flask was placed on the balance, and the mass of the flask and its contents were recorded every minute. The following graph was plotted. Name the gas produced. Now we had a reaction between what? Between hydrochloric acid, so HCl, plus calcium carbonate, CaCO3. So what gas would be produced because of this? Okay, so we don't need to necessarily know this. I had to search it up. So it will form CaCl2 plus CO2 plus H2O. So definitely the gas produced would be CO2, which is carbon dioxide. So A, the gas produced is carbon dioxide. B, what is the role of the cotton wool? Why do we need this cotton wool? We have a balance and we have the cotton wool. So if we have a balance and a cotton wool, the cotton wool is used for the gas to escape. So for part B, the answer is for gas to escape. Now, why does the mass of the beaker decrease? Logically, if the gas escaped, then the mass of the beaker decreases because gas escaped. On the same grid, sketch the graph if excess calcium carbonate powder was used at 50 degrees Celsius. We didn't use the limiting, so the slope will only change and not the plateau, so it will look something like this. Okay? Then, for part E, it says on the same grid, sketch the graph, okay, if concentrated hydrochloric acid was used instead at 50 degrees. So definitely the slope and the plateau will change, so it will look something like this. So again, I'll repeat D and E. D, we use the excess and we increase the temperature, so only the slope is being affected. Okay. And E, we used concentrated, so we increased the concentration of hydrochloric acid because before it was dilute, now it's concentrated at 50 degrees. So the slope will look something like this. So that was for question CQD 11. Now CQD 12. To prevent, the following apparatus is used to prepare, not to prevent, to prepare oxygen. A tube of 1 gram of powdered manganese oxide was added to the hydrochloric peroxide solution. Okay, so why was the tube of manganese oxide suspended in the flask? Because we want to separate the manganese oxide from the hydrogen peroxide. So before the reaction happens, we are gonna separate them. So to separate them, separate this and this. Part B. What is the role of manganese oxide? Manganese oxide is a catalyst. Why? Because it will react and speed up the reaction rate. So it is a catalyst, okay, speeds up reaction rate. Now, if 1 gram lumps of manganese oxide were used, what's the effect on the result? Because here we have powdered manganese oxide, they said 1 gram lumps. Okay, definitely the powdered have a larger surface area than the lumps, so lumps have a smaller surface area. Then the reaction rate will decrease if we have a smaller surface area. D. When the reaction stopped, 1 gram of catalyst was still left. Okay, why did the reaction stop? Why? Because all of this was used. We said manganese oxide is a catalyst, okay? And the catalyst will not be used. So the same mass of catalyst we had in the beginning, we will have at the end. But the reactants will be different than the products for sure. The mass is the same, but the reactants and the products are two different compounds or elements. Now the reaction stops because we used all of the hydrogen peroxide. Now they're telling us, how does this reaction start? We need the manganese oxide to go into the hydrogen peroxide for the reaction to start. So for it to start, we either let go of the string, because you see the string is holding it, or we shake the tube. So that's for CQD number 12. 23. Phosphorus P4 exposed to air burns spontaneously to give P4O10. The delta H of this reaction is negative 12321 kilojoules per mole of P4. Draw an energy diagram for the net reaction. Okay, since the delta H is negative, it is exothermic. So let's use this one. Okay, it's already an exothermic process. All right, we have our reactants. What is our reactants? It is P4 plus our oxygen, O2. All right. And so then it will give us what? P4O10 in our products. Is it balanced? No, we have 10 oxygen here, we have 2 oxygen here. So how do we make it 10? We add a 5 over here. So P4 plus 5O2 will give us P4O2. It's exothermic, right? So this is the energy diagram explaining the critical parts of the curve. Okay. Now, of course, the critical parts of the curve, this is the potential energy, this is the energy of the reactants, the energy of the products, the activation energy of the forward reaction, and then from, this is the heat of reactants and this is the heat of products. But here, from the reactants to the products, this is our delta H. All right? So that was for part A. For part B, how much heat is produced when 12.4 grams of phosphorus burns? What's the molar mass of phosphorus? The molar mass of phosphorus is 124 grams. Okay, this I used Google to get it. We're not supposed to know it. So 124 grams of phosphorus gives us 12321. Okay, negative 12321 kilojoules. All right. However, 12.4 grams will then give us negative 1232.1 kilojoules. This is stoichiometry, okay? But here they ask us how much is the delta H, or how much heat is produced, how much heat is given in the products. Now they asked us how much heat is given in the products. If they tell us produced, released, given, whatever, anything in these terms, formed, or anything in these terms, we will take the negative and we will change it to positive. So Since it's exothermic, we will have heat in our products, so the heat produced will become 2.1 kilojoules, not negative. So that was CQD number 23. Now CQD number 24. So CQD number 24, identify labels A, B, C, D, and E. A is the reactants, B is the activation energy, the forward activation energy. C is the activated complex. Okay, D is our products, and E is our delta H, or enthalpy change. Same meaning. The both of them are so it is the enthalpy change. That is part A done. Now give the effect of adding a suitable catalyst on each of the values of B and E. We said if we ever add a catalyst to a reaction, it will decrease. It will make the forward and backward reactions faster, so it will give us a lower activation energy. And so thus B decreases, alright, but E, it's not affected. E, which is delta H, is not affected. That was part B. Now CQD 27. Calcium carbonate reacts with excess hydrochloric acid, so calcium carbonate is the limiting, okay, to produce water, carbon dioxide, and a salt. Alright? Now, the rate of reaction is determined by measuring the volume of carbon dioxide gas released over time. Which of the following best describes the change of condition between the two experiments? Alright. We can see that they share the same plateau and they have different slopes. So there was nothing changed in the concentration of the limiting. So the temperature is higher in B than in A? Definitely not. The temperature is higher in A than in B because A has a steeper slope or a higher slope. Granulated calcium carbonate is used instead of powdered. So in B, they're telling us the surface area is less than in A. Definitely this is the case, so B is correct. C, a catalyst is used in B? No, catalyst was probably used in A. We said anything to do with the concentration of the limiting, which is calcium carbonate, we do not take it. So D and E, we do not take it because the plateau was not affected. So only if the concentration of the limiting was affected, then definitely the plateau is affected. Here it was not affected, so the concentration wasn't affected. So the correct answer is B. CQD 28 top. Question number 28. The rate of the following reaction can be increased by increasing the concentration of the hydrochloric acid solution. Which of the following statements is or are true about the reacting particles? 1. Collision rate of particles stays the same. 2. The proportion of particles with sufficient energy to react decreases. 3. The collision rate of particles increases. And 4. The proportion of particles with sufficient energy to react increases. Definitely, if we increase the concentration, they said they increased the reaction rate. Okay, if the reaction rate is increased, then the collision of particles increases. Alright, so definitely the proportion of particles doesn't decrease and it doesn't increase. Okay, and the collision rate changes, so the answer is 3 only, so C is our answer. Number 29. How does a decrease in temperature decrease the rate of a reaction according to the collision theory? As the temperature decreases, the collision of particles decreases and the proportion of particles with sufficient energy to react will decrease. Now, what's the difference between 29 and 28? Here, in 29, we increased the rate of the reaction by what? By increasing the concentration. So we didn't increase the temperature. Since we didn't increase the temperature, we didn't give the particles energy. We just added more particles, so they would collide more. So it's all about the keywords. Here we increased the concentration. Definitely the energy wasn't increased. Instead, the energy of the particles wasn't increased, instead the collision rate increases. Whereas here, we're decreasing the temperature, so the collision will decrease because the proportion of particles with sufficient energy will decrease. So that's CQD number 29. CQD 30 top. A student investigates the rate of reaction between excess magnesium and dilute hydrochloric acid. So the excess is the magnesium and the hydrochloric acid is the limiting. The setup of his experiment includes a syringe. A. The student collected the data and draws the graph below in order to describe the rate of the reaction. So this describes what? This is the slope of the reaction rate. If you remember in the previous video, we said if this is the slope of the reaction rate, then the measurement x is the time, on the x-axis is the time, and on the y it is the products. But what products to be specific? Since he is including a syringe, so he is collecting gas. So the products to be included here is a gas. And he is, with the syringe, he is doing what? He is measuring the volume of produced gas. So again, this is the rate of reaction. In the rate of reaction, measurement x is the time, and measurement y is the products produced. Now here he is including a syringe. So what is he producing? He's measuring what? The volume of the produced gas. So that's it for AI. Now AI. How does the rate of the reaction change as the reaction proceeds? So here it's increasing, so here it's fast. Why? It's a big amount of product produced in a small time, but then as you go up, it starts to slow down and then finally it stops. Now, let's explain it. To explain it, we say that the reaction gets slower because over time, the concentration of what? Of the limiting, our limiting is the hydrochloric acid. So the concentration of the limiting, okay, will decrease over time. And since the concentration is decreasing, what happens? There is less collisions. So that's A2I. Now, B. Another student performs the same experiment at a lower temperature. If he did it with a lower temperature, the reaction rate will decrease. So that's the impact of this change on the rate of the reaction. Now explain this change in the term of collisions as the temperature decreases. So temperature decreases. Then the kinetic energy decreases. Then if the kinetic energy decreases, then effective collisions decreases. Then since effective collisions decreases, our reaction rate will decrease. So this is in terms of collisions, why it changed. Now see, what's the effect of using smaller pieces of magnesium? Magnesium is our what? Magnesium is our excess. So if we're using smaller pieces, like it doesn't really matter because we're changing the surface area. The surface area means the pieces, okay? But I'm just saying in general, magnesium is our excess, okay? So if we're using smaller pieces, that means we are increasing the surface area, all right? And if we increase the surface area, then we will increase the reaction rate. So this is pretty much it for CQD 30. Now finally CQD 31, which I think is the last question. Yes, it is. So it is the last question of this chapter 9. Let us start. A student investigated the effect of temperature change on the rate of reaction between dilute hydrochloric acid and sodium thiosulfate. When these substances react, they form yellow sulfur. Okay, the time taken for sulfur to be formed using the same solutions but at different temperatures recorded. So this is experiment 1, and then experiment 2, experiment 3, and experiment 4. So let's read experiment 1. A paper with a marked cross was placed under a conical flask containing 10 centimeter cubed of sodium so that the cross is visible through the solution from above. 10 centimeter cubed of dilute hydrochloric acid was poured from a measuring cylinder into the container of sodium thiosulfate solution, and a chronometer was started at the same time. The temperature of the reaction mixture was measured and recorded. The chronometer was stopped when the cross mark cannot be seen anymore due to the formation of yellow sulfur. Formation of what? Precipitate. The final temperature of the solution was measured and recorded. The conical flask was emptied and rinsed with distilled water. Then experiment 2. A paper was marked across under the conical flask containing 10 centimeter cubed sodium thiosulfate. So the cross is visible through the solution from above. Then 10 centimeter solution of dilute hydrochloric acid was poured from a measuring cylinder into the container of sodium thiosulfate solution, and a chronometer was started at the same time. The reaction mixture was heated to 30 degrees Celsius. The chronometer was stopped when the cross mark cannot be seen anymore due to the formation of yellow sulfur. The final temperature of the solution was measured and recorded. The conical flask was emptied and rinsed with distilled water. Experiment 3. The student repeated the procedure followed in experiment 2, but the reaction mixture was heated to 45 degrees Celsius. And experiment 4, the students repeated the procedure in experiment 2, but the reaction mixture was heated to 50 degrees Celsius. So now, complete the data below by calculating and recording the average temperature and recording the time taken for the cross on the white paper to become invisible. So here we have the chronometer diagram, the time taken, the final temperature, the initial temperature, and the experiment number. So, for experiment 1, what was the average temperature? To find the average temperature, we're going to add the initial temperature and the final temperature and divide it by 2. Then we will get 19. What was the time taken for the cross on the white paper to become invisible? Look here, this is our seconds, this is our minutes. So it was 1 minute and 10 seconds. So 60 seconds plus 10 seconds, it was 70 seconds. In 2, the average temperature was 30 plus 28 divided by 2. It will be, let me do it on the calculator, 30 plus 28 divided by 2. We're going to get 29. Okay, and the time taken was 0 minutes and 50, 51, 52, approximately 52, I would say 52 or 53, I'm not sure, seconds. For experiment 3, we add 45 and 43, then we divide it by 2. Let me do it on the calculator. We get 44 is the average temperature, and the time taken was 0 minutes, but it was 30, 31, 32, I would say 32 or 33 seconds. All right, that was for experiment 3. Now for experiment 4, it was 50 plus 48 over 2 to find the average temperature. 50 plus 48 over 2. We will get then 49 is the average temperature. And then finally, the time taken was 0 minutes and 20 seconds. So that was for part A. Part B, draw a smooth line graph on the grid below, plotting results for the experiments 1 to 4. So let's go up again. I remember that here was 19, here was 29, here was 44, here was 49, and here was 70, 53, that's 70, 53, 32, and 20. All right, so that was what we need to remember to do the, to do part B. So now for part B, we need to plot. All right, how do we plot? We take for 70 seconds, so the time was 70 seconds, the average temperature was 19. So let us find 19. 19 was here. So for 70 seconds, it was over here approximately. Then for 53 seconds, it was 29. So we go to 29, which is over here. We go to 53, so here is 53 and here is 29, so they will meet over here. Then I'll change the color. At 32 seconds, it was 44. So here's 32, and over here is 44. So, no, wait, it's not accurate. 32 is over here, and 44 is more here, I would say. So this is 32.44, and finally at 20 seconds it was 49 degrees. So at 20 seconds we find the 49 degrees. It was approximately here. So if you notice, it is a straight line. So this is how we plot. Part C. Use your graph to deduce the average temperature needed for the cross mark not to be seen after 60 seconds. So, bad thing we removed the graph. Let me redraw it again. So this was the graph we had from before. They're telling us to find at 60 seconds the average temperature. So let's go 60 seconds here. Or no, let me draw more accurate. Be here. And then actually it increases from here. So I'm not really sure. I would say 25 degrees Celsius, or if it's inaccurate, it would probably be 26 degrees Celsius. So probably in the graph, definitely in the exam, it will be more accurate. Not like this. But for me, what I got was either 25 degrees Celsius or 26 degrees Celsius, because as you see, it's, you know, here and there. So, yeah. That was for part B. It's either 25 or 26 degrees Celsius. Now, sorry, that was for part C. Now for part D, identify the experiment at which the rate of reaction was lowest. Basically, which experiment ran at the lowest temperature? It was experiment 1. Because it ran at the lowest temperature, okay, the kinetic energy was definitely the least, so they would move slower, causing a less efficient collision. And then finally it would then decrease into reaction rate being slowest. So that was for E. For F, the use of pipettes or, oh my goodness, no, sorry, that was for D, I missed E. For E, a student added hydrochloric acid to sodium thiosulfate solution using a pipette instead of the measuring cylinder. Now, they're telling us that the student used a pipette instead of a measuring cylinder. Even though the pipette is more accurate, all right, the measuring cylinder, okay, you can put them all in one go, whereas the pipette will take a longer time to put the hydrochloric acid. So then the reaction rate will be slower because he's putting it one drop at a time, whereas in the measuring cylinder he can put it directly all in one go. So that's for E. And now finally for F, the use of pipettes or burettes to measure volumes of the solution used in these experiments would improve the accuracy of the results. Suggest another way to improve the accuracy of the results of these experiments. Definitely, he's doing this in a place in like, where is he doing this, student? He's probably doing it in the lab, okay? So in the lab, for sure, there will be heat loss from the surroundings. And they said, other than measuring the volumes of these solutions to improve the accuracy, we need another way. So instead of losing the heat to our surroundings, we could use an insulation that would keep heat or temperature constant. So that was it for what's this, chapter 9. I hope you guys didn't get bored and that you made it to the end of the video, because me myself, I lost my voice explaining. Okay, thank you guys for watching and have a wonderful day.